The well-known closure statement of the second law of thermodynamics asserts, "It is impossible to construct a device that, operating in a cycle, has no effect other than the transfer of heat from a cooler to a hotter body." Thus, the closure statement tells us that energy will not flow from cool to hot regions without outside assistance. The devices that provide this help are called refrigeration units and heat pumps. Both types of devices satisfy the closure's requirement of external action through the application of mechanical power or natural transfers of heat. The distinction between refrigerator and heat pump is one of purpose more than technique. The refrigeration unit transfers energy from cool to hot regions for the purpose of cooling the cold region, while the heat pump does the same thing with the intent of heating the hot region. It should be pointed out that any heat engine cycle, when reversed, becomes a refrigeration cycle because the cyclic integral of the heat transfer, and thus the network, becomes negative. This implies heat rejection at higher than the lowest cycle temperature. This video presentation will focus on refrigeration, specifically the vapor compression refrigeration system. But first of all, what is refrigeration? From its formal definition, refrigeration is the process of removing heat from an enclosed space or from a substance for the purpose of lowering the temperature. Refrigeration is best known for its use in the air conditioning of buildings and in the treatment, transportation, and preservation of foods and beverages. It also finds large-scale industrial application, for example, in the manufacture of ice and the dehydration of gases. Applications in the petroleum industry include lubricating oil purification, low temperature reactions, and separation of volatile hydrocarbons. Meanwhile, the vapor compression refrigeration system is the mainstay of the refrigeration and air conditioning industry. Now, let's take a look on how a vapor compression refrigeration system works.
The vapor compression refrigeration system is by far the most popular and widely used in refrigeration. The system uses working substance or refrigerant like ammonia, R11, R12, and R22. System mainly consists of four parts: compressor, condenser, expansion valve, and evaporator. When compressor is started, it draws the low-pressure vapor from the evaporator at 1 and compresses it isentropically high pressure up to 2. Hence, vapor temperature also increases. Hot vapor from compressor to condenser, when it is cooled, rejects heat and hot vapors get converted into liquid. Then it is passed from expansion valve, which reduces pressure of liquid. Thus, liquid gets converted into vapor of low dryness fraction. Finally, low pressure, low temperature refrigerant passes through evaporator, where it absorbs its latent heat from cold chamber and gets converted into vapor. Thus, cycle is completed. Still confused? No worries. To have a better perspective of the principle, let us try to solve a problem. A vapor compression refrigeration system with a capacity of 10 tons has superheated refrigerant 134A vapor entering the compressor at 15 degrees Celsius, 4 bars, and exiting at 12 bar. The compression process can be modeled by P times V raised to 1.01 equals to constant. At the condenser exit, the pressure is 11.6 bar and the temperature is 44 degrees Celsius. The condenser is water-cooled, with water entering at 20 degrees Celsius and leaving at 30 degrees Celsius with a negligible change in pressure. Heat transfer from the outside of the condenser can be neglected. Determine the mass flow rate of the refrigerant in kilogram per second, the power input and the heat transfer rate of the compressor, each in kilowatts, and the coefficient of the performance.
Shown on the TS diagram are the four steps of the process. The vapor compression refrigeration cycle is represented in the schematic diagram. The vapor produced from the evaporator is compressed to a higher pressure and is then cooled and condensed with a rejection of heat at a higher temperature level. Liquid from the condenser returns to its original pressure by an expansion process. In principle, this can be carried out in an expander from which work is obtained, but for practical reasons, is usually accomplished by throttling through a partly open valve. The line 1-2 represent the actual compression process, slopes in the direction of increasing entropy, reflecting inherent irreversibilities. The line 3-4 represents the throttling process, which occurs at constant enthalpy. Meanwhile, the line 4-1 occurs at constant pressure, which provides a means for heat absorption at a low constant temperature. For this model, each component is analyzed as a control volume at steady state. The compression is a polytropic process, given the condition that PV raised to 1.01 is constant. The expansion through the valve is a throttling process. Heat transfer from the outside of the condenser can be neglected, and kinetic and potential energy effects are negligible.
In this problem, we are going to present two solutions. One is based from Paris Chemical Engineering Handbook and from Fundamentals of Engineering Thermodynamics by M.J. Moran and H.N. Shapiro, 5th and 2nd edition.
Through interpolation from the Paris Handbook, Table 2-278, Thermodynamic Properties of R134A, given the pressure is 4 bar and temperature is 50 degrees Celsius, we can get the values of H1 and V1, which are 407.0552 kilojoule per kilogram and 0.0425 cubic meter per kilogram. State 2. After compression, which is a polytropic process, given the condition that PV raised to 1.01 is constant, we will have the formula P1V1 raised to 1.01 is equals to P2V2 raised to 1.01. Equating it to V2, we will have the formula V1 times the quantity of P1 over P2 raised to 1 over 1.01. Then we can have the value of V2, which is 0.0143 cubic meter per kilogram. And then through interpolation at P2, which is 12 bar, and V2, which is 0.0143 cubic meter per kilogram, we will have the H2, which is 4.22.01113 kilojoule per kilogram. Upon exiting the condenser, the new temperature will be 44 degrees Celsius, and through interpolation at saturated liquid, we will have H3 is equals to 262.4896 kilojoule per kilogram. Lastly, for the throttling process wherein enthalpy is constant, the H3 will be equal to H4, which is equal to 262.4896 kilojoule per kilogram. So after we obtain the necessary values for various constants, we will now proceed to the calculation of what is being asked in the problem. First of which is the mass flow rate of the refrigerant. To design the evaporator, condenser, compressor, and auxiliary equipment, one must know the rate of circulation of the refrigerant, denoted by M. And this is determined by the rate of heat absorption in the evaporator by the equation Q equals M times H1 minus H4. But before we go straight to the calculations, let me first give you a quick trivia. You might be wondering why the capacity of this refrigeration system is rated in terms of tons. Well, this is because in the United States, the refrigeration equipment is commonly rated in terms of tons of refrigeration. And a ton of refrigeration is defined as the heat of absorption rated at 12,000 BTU per hour or 12,660 kilojoule per hour. And this corresponds approximately to the rate of heat removal required to freeze a ton of water, initially at 32 degrees Fahrenheit per day. And now let's go back to the calculations. We will now substitute the necessary values such as the capacity, the enthalpies for the state 1 and 4, and the conversion factor, which comes from the one I have mentioned in the trivia. And upon simple division, this will give us a value of 0.2433 kilogram per second as our mass flow rate. And for letter B, we are asked to find the power input and the heat transfer rate for the compressor. And in order to find the power input, we will now be utilizing this equation, and upon substituting the known values, we will obtain the work input for the compressor, which is 18.7824 kilojoule per kilogram. And now we will proceed to the calculation of the power input for the compressor. We will just multiply the work input with the mass flow rate we have obtained earlier, and this will give us a value of 4.5690 kilowatts. And for the heat transfer rate, we will now be employing the energy balance equation, and it is assumed that kinetic energy and potential energy are negligible. And cancelling those out will leave us with Q equals negative W plus M delta H. And substituting all those known values will give us a value of negative 0.9308 kilowatts. Lastly, we will measure the effectiveness of the refrigerator, that is, the coefficient of performance given by Q over W, which is the heat absorbed at lower temperature over the power input for the compressor that is calculated a while ago. And again, upon substitution, this will give us a value of 7.6969.
By interpolating the values of H1 and V1 from table 8-13, using the state 1 conditions, 4 bars and 15 degrees Celsius, we will get a value of 258.155 for the H1 and 0.05258 cubic meter per kilogram for the value of V1. Moving on at the state 2 after the compression process, wherein the new pressure is now 12 bars, we can solve for the value of H2 by solving first V2 by using the condition PV raised to 1.01 is equals to K. And now we can let P1 V1 raised to 1.01 equals to P2 V2 raised to 1.01. And now we can substitute the known values, which is V1 0.05258 cubic meter per kilogram and P1 4 bars and for the P2, which is 12 bars, and the resulting value for V2 is 0.01772 cubic meter per kilogram. And now, we can interpolate the value of H2 from the same table, E-13, using P2, which is 12 bars, and V2, 0.01772, and the resulting H2 is 281.3187 kilojoule per kilogram. And now for the state 3, after passing through the condenser, the H3 is now based on the saturated liquid. Since the refrigerant is water-cooled, the output is in the liquid form. And now we can get the value of H3 from the table named Saturated Refrigerant 134A temperature table. We can use the temperature in the state 3, which is 44 degrees Celsius, and the resulting enthalpy would be 112.22 kilojoule per kilogram. So for the last part, which is the throttling process, since the refrigerant is passed through the throttling bulb, H3 is equals to H4. So H3 has the same value of 112.22 kilojoule per kilogram.
After solving for the enthalpies on each state, we can now solve for the required data. First one is the mass flow rate of the refrigerant in kilogram per second. We can determine this by using the formula capacity is equals to the mass flow rate multiplied with the difference between the enthalpy 1 and enthalpy 4. Rearranging this formula, we can get mass flow rate is equals to the capacity all over the difference between enthalpy 1 minus enthalpy 4. Substitution of the known values, we can get our mass flow rate 0.24097 kilogram per second. We are also required to get the power input. But before we get the power input, we should first solve for the work input. The formula to be used is n over n minus 1 multiplied by P2 V2 minus P1 V1. Since n is greater than 1.01, that is called the polytropic process. We're going to use this kind of formula. So now, we're going to substitute all the known values in the formula, which is this. We can get now the work input 23.432 kilojoule per kilogram. Now, to solve for the power input, we will multiply the work input to the mass flow rate. So substitution of the values, our power input now, compressor power input is 5.6465 kilowatts. We are also required to get the heat transfer in the compressor. So we can determine the heat transfer using this formula. Negative value of the power input plus mass flow rate multiplied by the difference between enthalpy 1 and enthalpy 4, and substitution of the known values, our heat transfer rate is negative 0.06405 kilowatts. Lastly, we are required to get the coefficient of performance, or the COP. The formula for COP is the capacity over the power input. So substitution of the known values, we have 6.2280 coefficient of performance.